So hello everyone. So we had a brief introduction about second law of thermodynamics in case of previous video lecture. Regarding this current video lecture concern, we are going to have some in-depth discussion of uh, problem focused, right? So straight away I'm leading you towards numerical problems on heat engine, refrigerator, and heat pump based, right? So this is the very first problem. Again, we are dealing with the same problem what we had in the previous video lecture, right? A heat engine which receives heat at the rate of 1500 kilojoule per minute and gives an output of 8.2 kilowatt. Determine the thermal efficiency and the rate of heat rejection, right? So with two given data, we are supposed to find two unknowns. One is thermal efficiency and another one is rate of heat rejection. We all know based on the keyword of heat engine, we used to draw a diagram of this manner, starting from the high temperature source at the top and a sink at the bottom, connected by a transfer function called heat engine, right? This is a simple modification of the general diagram what you had in case of previous slides, right? Q1 represents heat supplied, Q2 represents heat rejected, right? For the supplied heat of 1500 kilojoule per minute, the heat engine recorded work done as 8.2 kilowatt, right? Now the question is, we are in a situation to answer thermal efficiency of this heat engine, followed by determination of Q2, which is rate of heat rejection. So based on the mark, the question belongs, right? We need to elaborate given data as well as formula to be used this graphical illustration in a detailed manner, right? So in the very next slide, we are having the solution straight away. Uh, it's been our responsibility to convert kilojoule per minute into kilojoule per second, right? Any heat transfer is going to be expressed in terms of kilojoule per second. For that, we are dividing the provided value of 1500 by 60. Just imagine if the value is given in the unit of kilojoule per hour now, we need to divide it with 3600, which is 60 into 60, right? Here we are having kilojoule per minute, so we are dividing it only with 60, which gives the value of 25 kilojoule per second. Then comes work output. Straight away, the work output is given in kilowatt. We can equal the same with 8.2 kilojoule per second, right? We all know the thermal efficiency formula of heat engine is work done at the output to the ratio of heat supplied at the input, right? That is simply W by Q1. So 8.2 divided by 25, which yields 0.328. For better representation of this 0.328, we are multiplying it with 100. Any value you obtained in the form of efficiency, right? You are going to multiply 100. We are going to standardize those value for the range of 100. Anyhow, you are going to have some value less than 100 only. That is the key representation of second law of thermodynamics. Efficiency of any heat engine won't cross efficiency of not only the heat engine, any thermal system won't cross 100 percentage, right? So here 32.8 percentage is the answer. And then comes the second to find category is rate of heat rejection, which is Q2. We all know the formula for calculating W from the very first general diagram is W is equal to Q1 minus Q2. Here, in case of the current problem, we know we are provided with Q1 as well as the value of W. So straight away, we are applying the value of Q1 and W simply by rearranging the formula W is equal to Q1 minus Q2. By having Q2 on our left hand side, we are having Q1 minus W on our right hand side. On substituting the provided values, we are able to have the value of 16.8 kilojoule per second as the rate of heat rejection, right? So this is how numerical problem one has to be answered. Now coming to the second numerical problem, which is based on refrigerator. As we discussed earlier in the class, it's a mere modification, a reverse format of heat engine, right? So we are in a situation to find coefficient of performance. Obviously, the core objective of any refrigerator is to remove heat from the vessel or material kept inside. That governs the output. For refrigerator as well as heat pump, work has to be supplied to the system. We can't expect work done by the system, right? So the arrow mark is towards reversed heat engine, which is simply a refrigerator here, right? Then comes source of the refrigerator is evaporator, obviously. That is why it's being given as evaporator. Then comes the sink is the condenser. That is why it is given as T1, right? So here comes the uh, given data concern. Find the coefficient of performance and heat transfer rate in the condenser of a refrigerator in kilojoule per hour, which has a refrigeration capacity of kilojoule per hour. As we discussed in previous problem, we dealt with kilojoule per minute, right? Here, in case of the current problem, we are going to deal with kilojoule per hour. So simply on, uh, we have to convert that into kilojoule per second based on the requirement. When power input is 0.75 kilowatt, right? So either you have to convert this kilojoule per hour into kilojoule per second, or else you need to convert this kilowatt into kilojoule per hour. That will give you an unitless COP, right? COP as well as efficiency are going to be unitless, right? Either you have to convert this kilojoule per hour into kilojoule per second, or else you need to go for an attempt of converting this kilowatt into kilojoule per hour, right? Here, in case of our PK Nag, sorry, RK Rajput concern, they convert, they retained this kilojoule per hour and attempted conversion of this kilowatt into kilojoule per hour simply by multiplying it with 3600, right? We all know COP of refrigerator formula is heat absorbed at low temperature, which is heat rejected divided by work input, right? Q2 value is 12,000 as given in the problem. Then comes the W value 0.75 into 60 into 60, which is 4.44. And we all very well know about the W formula of refrigerator. That is also been discussed in case of the very first slide itself, right? The formula for calculating W is Q1 minus Q2. Q1 is heat supplied and Q2 is heat rejected, right? So on rearranging that formula, we are having Q1 is equal to Q2 plus W. 12,000 plus 0.75 into 60 into 60, which gives value of 14,700 kilojoule per hour, which is the heat transfer rate, right? So this is how the problem 2 has to be answered. While going for somewhat a complex problem, which is of worth 16 marks, as we discussed in the class, let me repeat the same problem. Here, the output of reversible heat engine is connected to a reversible refrigerator. Okay. Heat engine operates between a reservoir of 700 degrees Celsius and 50 degrees Celsius, while the reversible refrigerator driven by the output of heat engine is operating between 50 degrees Celsius and minus 25 degrees Celsius, right? In addition to that of four temperatures, heat transfer to the engine, that is heat supply is provided, and the net work output of the combined engine refrigerator plant, overall W, capital W is given as 400 kilojoule. We all know formula for calculating W is W1 minus W2 in case of this combined scenario. Now, based on the given data, at first we are in a situation to determine heat transfer to the refrigerant, heat transfer to the refrigerant, and the net heat transfer to the reservoir at 50 degrees Celsius. By reconsidering point 1, given that efficiency of the heat engine and the COP of the refrigerator are 45% of their maximum possible value, right? For this, first, we are going to straight away apply efficiency of heat engine formula, for which we had two formulas. One is W by Q1. Here in this case, we need to understand the graphical illustration of this combined thermal system, while the output of heat engine, that is work done by the heat engine, is used to drive or supply power input to the refrigerator system, while the given data are presented accordingly: T1, T2, and T3, right? Heat supplied is 2500 kilojoule with reference to the problem statement. Then the overall work done is also mentioned. We simply present it wherever we are in need of, right? Totally, there are four heat transfer involved, out of which we are provided with the values of Q1, as well as we all know the formula of heat rejected in case of refrigerator plant, where in case of earlier we had, right, Q1 is equal to Q2 plus W. This is what we witnessed in case of the previous problem also. Q1 is equal to Q2 plus W, while in case of the current problem, the interaction is between 2 and 3. That is why we are having Q2 is equal to Q3 plus W here, while the interaction is between Q3 and Q4 here, right? Q3 and Q4 here. That is why we are having the rearranged formula of the previous one as Q3 is equal to Q4 plus W2, right? So there are two efficiency formula for heat engine. If it is specified as maximum, then we need to make use of the formula called T1 minus T2 by T1, or else 1 minus T2 by T1, right? Also, the general efficiency formula as W by Q1. Please try to differentiate maximum efficiency with the general efficiency, right? If it is maximum mentioned, we are going to make use of temperature based formula. If it is mentioned generally as an efficiency, now we are going to make use of simply the ratio of work done to the top heat transfer, heat supplied formula, right? So based on the given data, we are substituting the given data sets to obtain the maximum efficiency as 0.668. Now we are equating this 0.668 with the general efficiency formula W1 by Q1, where Q1 is also provided. On rearranging this equation, the value of W1 can be obtained. Similarly, for refrigerator also, there are two types of COP formula. One is COP max and the another one is COP general. If it is COP general, in line with the heat engine, we are going to have ratio of heat rejected to the top work done. If it is COP max, again we are going to make use of a formatted temperature formula T3 by T2 minus T3. On substituting the available temperature here, again we are going to equate with the general COP formula, based on which we are able to compute the required heat transfer rate wherever we want. We all know W1 minus W2 is equal to W, which is of 400 kilojoule. Now, based on the computed value of 1670, we are able to have the value of W2. Then, on having the value of W2, we can go for computation of Q4, right, as 4198.6 kilojoule. On obtaining the value of Q4, we can go for the computation of Q3 using this formula, where we are having the value of Q3 as 5468.6 kilojoule. At last, on having the value of Q3, we are able to fill the space wherever we want. Generally, Q2 is equal to Q1 minus W1. This is already computed in case of previous one. That is why we are substituting straight away here. 2500 is given in the problem itself, while W1 is computed here in the step, which is 830 kilojoule. Now, the heat rejection to the 50 degrees Celsius reservoir Q2 is, right, Q2 plus Q3 put together. This is heat rejected to the reservoir from the heat engine side, and this is heat rejected by the refrigerator towards what? Heat rejected to the reservoir from the refrigerator end, right? So we are summing Q2 plus Q3 as 830 plus 5468.6, which yields you the combined value of 6298.6. As mentioned clearly in the problem itself, right? Refrigerator operates between reservoir at a temperature of 50 degrees Celsius and a minus 25 degrees Celsius, right? The common 50 degrees Celsius for both heat engine and the refrigerator is mentioned here, while the minus 25 degrees Celsius from 273 Kelvin is listed here. Please try to differentiate. Then comes the second class identification. By reconsidering 0.1. Now we are in a situation to calculate efficiency of the heat engine and COP of the refrigerator, right, for the maximum possible values. Now we are going to equate computed efficiency in case of previous endeavor. The efficiency value is going to be mapped here with maximum of 0.45 value, right? So efficiency is equal to 0.45 of maximum efficiency, which is 0.668 from the previous slide we are having, right? On substituting here, the efficiency will come around 0.3. Simply, on rearranging the general efficiency formula, we will have W1 is equal to efficiency into Q1, while efficiency from here is going to be substituted here, and the Q1 from the given data is 2500. We are having the value of 750 kilojoule. Now the W2 becomes 750 minus 400, which is 350 kilojoule. Now, what happens if 45% of the maximum possible value for refrigerator case concern? Here, we all know there are two types of COP formula. There are two types of efficiency formula. The general formula is Q by W or W by Q in terms of heat engine. In case of refrigerator, it is Q by 4, Q4 by W2, right? On equating this with this 0.45, we are having the value of 1.48. This Q4 by W2 is already mentioned here as 3.306, right? So on rearranging this, once again, we are able to compute what? Q2 plus Q3 as 2618 kilojoule. By assuming 45% of the maximum possible value, we are having the total heat rejected to the 50 degrees Celsius reservoir is 2618, while it is in case of previous endeavor is 6298.6 kilojoule, right? So this is how we need to deal with a complex problem, which is of worth for a 16-mark question, right? Then comes a need for the fourth case of a problem. While the first three problem dealt with arrangement of heat engine parallelly, right? This is one among the important problem where we are going to have two Carnot engine work in series between the source and the sink temperature, which is of 550 Kelvin and 350 Kelvin. If both engine develop equal power, determine intermediate temperatures, right? The key difference between the previous endeavor and the current one is, in line with the previous problem, it's going to be two reservoir only, right? But than that of connecting heat engine in parallel, in case of the current problem, we are going to connect heat engine in series. So we are going to rearrange heat engine one above the other, right? Like what we are having in the left side graphical illustration. So only two data sets are provided. One is T1 and another one is T2. And as mentioned, two heat engines are connected in series. In line with the previous problem, heat engine is expected to be supplied with heat and is expected to deliver some set of work done. The amount of heat rejected by HE1 is provided as heat supplied to HE2, while for the supplied heat, HE2 will also provide some sort of work done. Once again, HE2 will also discharge some heat towards the sink, right? So this is the state where we are provided with the value of T1 and T3. We are in a situation to calculate the intermediate temperature denoted by the symbol T2, right? For this, which specified in the previous case, there are two types of efficiency formula. One is efficiency max and another one is the general efficiency. Here we are going to make use of the general efficiency formula, which is simply if it is in terms of 1 na W by Q1, if it is in terms of 2 na W by Q2, again we are going to equate this with the maximum efficiency T1 minus T2 by T1, while in case of 2 to 3 na T2 minus T3 by T2, right? We are just equating efficiency with efficiency max, right? As a mean of which we are going to have W divided by Q2 plus W. We all know W is Q1 minus Q2, right? For calculating Q1, we can rearrange the equation in terms of Q2 plus W. Likewise, we may also have the interaction between Q2 and Q3 as Q3 plus W, right? Now, just consider the equation 1 where you are going to cross multiply Q2 plus W with this T1 minus T2 divided by T1. Then you are going to multiply Q2 with this T1 minus T2 divided by T1 plus W into T1 minus T2 by T1. On taking W as common, you will have some 1 minus T1 minus T2 divided by T1, which is equal to Q2 into T1 minus T2 divided by T1. On rearranging this equation, you will have W as Q2 into T1 minus T2 divided by T2, right? Similarly, you are supposed to cross multiply this from equation 2 to have a final output of this nature. Please try to uh, match equal the inputs what we had, the final results what we had from equation 1 and equation 2, thereby which you are able to cancel T2 on the left hand side as well as on the right hand side, right? On equating the things, you are able to calculate what? The final value of T2 as 450 Kelvin based on the available T1 and T3, 550 and 350 respectively. Thus, this is how the intermediate temperature has to be computed. So, with this, problems based on heat source and sink of heat engine type, reversed heat engine types, namely heat pump as well as refrigerator are to be dealt with. In case of any clarification, feel free to contact me, thereby which you will be directed in the right way, right? Next, I'm leading you towards numerical problem based on Clausius inequality. We all very well know that Clausius inequality is ratio of cyclic integral, which is of ratio happening between rate of heat transfer with the absolute temperature, right? Less than or equal to zero. The ratio is equal to zero in case of reversible process, and the ratio is less than zero in case of irreversible process. Using the simple formula, we are going to deal with problem of this nature under the manner of Clausius inequality. So 300 kilojoule per second of heat is supplied at a constant temperature of 290 degrees Celsius to a heat engine. The heat rejection takes place at 8.5 degrees Celsius. The following results were obtained. 215 kilojoule per second are rejected, 150 kilojoule per second are rejected, 750 kilojoule per second are rejected. Totally, there are three cases. For these three cases, we are going to recommend whether the process is reversible, irreversible, or impossible, right? So, for this, we are going to rewrite the given data from the question, right? Heat is supplied at the constant temperature of 290 degrees Celsius. Heat supplied is 300 kilojoule per second. Then comes heat rejection takes place at 8.5 degrees Celsius. QR. Three different values of QR are given 215, 150, and 75. We all very much familiar with this Clausius inequality formula. Now we are going to substitute del Q as 300 as mentioned as heat supplied here. Then comes the temperature 290 plus 273. On substituting this in our left hand side to the top heat rejected, the very first heat rejected provided 215 divided by 8.5 plus 273. So 0.5328 minus 0.7637. This deals with heat supplied and this component deals with heat rejected. Difference between this heat supplied and heat rejected is the value of heat rejected is greater than that of heat supplied. That is what we are having the value of minus 0.2309, which is obviously less than zero. If it is less than zero, na, the cycle is irreversible. Now we are going to keep this heat supplied terminology constant for case 2 as well as case 3. We are going to change the numerator of the heat rejection as given here 150 is 75. As a mean of which here in case of case 2 both are equal, then it becomes 0. From the previous slide itself, we know if Clausius inequality is equal to 0, na, then the process is a reversible process. If it is greater than 0, na, it becomes what? Impossible, and that governs what? the real Clausius inequality. So this kind of problem alone is eligible from the side of Clausius inequality to have in 8 mark or a 16 mark based on the question paper setter, right? So the very next topic is entropy based calculations. For this, we have to be very much comfortable with this formula table, right? At first, the general case related formulas were given, the formula in terms of T and V, P and V, and T and P. Then comes constant volume formula, constant volume process based del S formula, constant pressure based del S change of entropy formula, followed by isothermal, adiabatic, and polytropic, right? You may have a general problem of this nature. Simply on understanding this problem too, you are able to solve problem one in an easy manner, right? You will be provided with a clue. Say, for example, in case of problem one itself, we are provided with a clue called PV power n is equal to constant. A typo error happened here, a kind excuse for that, right? So PV power n is equal to constant. Now, obviously, we have to be very much aware of this formula, right? Simply, we are going to make use of this formula to have what? The final answer. Likewise, in case of problem 2, we are provided with some set of given data. A rigid cylinder containing 0.004 meter cube of volume and 1 bar pressure at 300 Kelvin. These are all the initial condition data sets. Is heated reversibly until temperature become 400 Kelvin. Now determine QS, entropy change. Assume nitrogen to be a perfect gas. Now we are going to deal specifically with the nitrogen. The problem may be slightly varied by introducing few more chemicals in place of nitrogen. So don't try to memorize this kind of problems at any cost. Simply you are going to identify what kind of problem it is. Clearly, from the determination column, it is mentioned that you are in a situation to find change in entropy, right? Now, to find the value of change in entropy, we are in need of MCV log E T2 by T1. Once again, this is also a polytropic process, right? Once again, this is also a polytropic process. The entropy change formula for the polytropic process is M into CV into log E T2 by T1. While you are able to witness T1 and T2 in the question itself, but it is not clearly mentioned the value of CV. We all know from the unit 1 the formula to calculate CV. Once the value of gamma is given as CV is equal to R by gamma minus 1. Then you may have a question. Sir, the value of gamma is given. What happens to R? The R has to be calculated based on a formula called R naught by M. While the R naught stands for universal gas constant, which is 8.314, divided by M is the molecular mass, which is 28 for nitrogen. We all very much comfortable with the molecular mass of nitrogen, right? On substituting this value, we'll have the value of 0.297 kilogram per kilogram Kelvin. Then comes PV is equal to MRT formula, and rearranging PV is equal to MRT in terms of M on our left hand side, we will have the rearranged formula of this nature. Then we are able to compute what? The mass also. So simply on having the value of mass and R, we are able to deal with the CV calculation. CV calculation is very easy once the R is known. Gamma is also 1.4 given. If it is not given, please assume that as 1.4. This is how we are calculating. We are going to calculate CV. Then comes the heat supplied, which is the very first one to be determined. We all know Q is equal to MC delta T. Here it is a constant volume process. That is why M into CV into T2 minus T1. M, this is what we calculated using PV is equal to MRT formula. CV, what we calculated using R by gamma minus 1. Right? T2 and T1 are directly given in the question paper. And now we are going to calculate change in entropy. So once this CV and M are calculated using this R, calculation of change in entropy is very easy, right? So this is how you are supposed to have problems on change of entropy also. So in case of unit 2, you are going to have three classes of problem. One based on heat source and sink, second one based on Clausius inequality, and the third one based on change of entropy. So it's been your choice to deal with the time what you are going to take for your preparation matters a lot. For any further classification, for any further clarification, please do approach me in person, or else please make your comment here. That way which we will have further interaction for better understanding of the subject. Thank you so much. See you again in some other video. Thank you.